Okay, so get ready to explore the universe a little deeper today because we are diving into dark matter.
Hmm.
And you have sent some seriously cool research. I've got to say, just looking over this stuff, I'm hooked already.
Well, strap yourself in because we're about to unpack something that makes up like 85% of the universe's matter, but we can't even see it.
Yeah, right. It's like this massive cosmic riddle. It's hiding in plain sight. And the way we can even tell it's there is fascinating to me. Like, it's all about gravity, those invisible strings that kind of pull everything together.
It's true. And the coolest thing is we can see how dark matter affects galaxies, even like whole clusters of galaxies. But we still haven't seen the stuff itself.
It's like, there's a giant elephant in the room, but you can't actually see it. You just see its footprints, maybe feel its breath.
Exactly. And that is where this research you sent comes in. We've got these papers. Some are about the latest experiments trying to find a dark matter particle, but then others, they're going deep into the theory, like mind-blowing ideas about what this dark matter stuff could be.
And speaking of mind-blowing,
Yeah.
one paper actually uses a really cool analogy to explain what the universe is made of. They use a chocolate cupcake.
Oh, yeah.
And I got to admit, when I saw that, I was like, okay, I'm on board. Let's do this.
That's a good ology.
So picture this. You've got your cupcake, right?
Yeah.
And the actual cake part, the main part, that's dark energy, the mysterious force that makes the universe expand. The frosting is holding it all together, and that's our dark matter. It's providing that gravitational glue for galaxies.
Yeah.
And last but not least, the sprinkles. That's us.
Ah.
All the regular matter that we see and touch every day, which is really just a tiny part of the whole cosmic dessert.
I like it. It's a good analogy. But you know what I really thought was cool is that the paper, it actually talks about how these models, even though they're simple and help us visualize, they can only go so far. Like, it's good to remember that we're still trying to figure out the real deal, what makes up that dark matter frosting.
It's true. It's like we're still trying to figure out the recipe, and it gets even more wild when you look in the evidence. One of the biggest clues we have about dark matter is something called galactic rotation curves. Imagine like a merry-go-round. The horses on the edge, you'd expect them to be moving faster than the horses closer to the center, right?
Right, yeah.
So, in a way, galaxies are kind of like giant merry-go-rounds. Stars are swirling around the center. But here's the thing. If we only look at the matter we can see, like stars and gas, those stars way out on the edge should be moving slower, but they're not.
Yeah, it's like they're breaking the rules.
Totally. And it's not just one galaxy doing this, it's almost all of them. And this is where things get really interesting. Because the only way those outer stars can be moving that fast, like racehorses on this cosmic carousel, is if there's way more gravity than we can see.
It's like those stars are holding on to an invisible merry-go-round, and that's our dark matter.
Exactly. Enter the cosmic scaffold, this halo of dark matter that we think surrounds galaxies,
Yeah.
and it's keeping them from flying apart. But then the big question is, what is this halo actually made of?
Yeah, that's the million-dollar question, right?
Right. And for the longest time, the best guess was a particle called a WIMP, short for weakly interacting massive particle. Imagine, like a ghost particle, it doesn't really interact with light or regular matter, but it's got mass, so it has gravity.
It seemed to fit, too, right? Like they would have been created in the early universe in just the right amount to explain the dark matter we see. Plus, some physics theories already predicted they existed.
It was like the perfect suspect. They
Yeah.
had the motive, and it matched the evidence. So scientists built these incredibly sensitive detectors, some of them underground, and they're trying to catch a WIMP.
Yeah.
They want to see this tiny little burst of energy, like when a WIMP bumps into an atom.
Like a game of cosmic billiards.
Exactly.
Ugh.
But here's the catch. Decades of searching, better and better detectors,
Yeah.
and nothing. No WIMPs, or at least none that we've been able to detect yet, which honestly has got to be both frustrating and exciting for these scientists.
Right. You dedicate your career to finding this thing, this particle, and silence. Makes you wonder if we're even looking in the right place.
It really does make you wonder, like, do we need a whole new set of suspects? And the cool thing is, there are all these other possibilities out there just waiting to be explored.
Oh, yeah, for sure. And while everyone was focused on the WIMP, other theories were always there in the background. There's this one particle called the axion.
Axions, right. I think I remember seeing that in the research. But aren't those even more ghost-like than WIMPs?
Yeah.
How can you even look for something that barely interacts with anything?
Okay, so imagine you're setting a trap, right? But instead of catching something like a mouse, you're trying to make a particle show itself. One really cool method is to use something called a haloscope. It uses powerful magnetic fields to try to get axions to, like, transform into photons, little particles of light.
Interesting. So it's like luring the particle out with its favorite treat.
Mm.
And if you catch an axion, it wouldn't just be huge for dark matter, it would also solve a totally different problem in physics called the strong CP problem.
Okay.
Okay, now you got to explain that one. What is the strong CP problem, and how does the axion come in?
Well, basically, it's this puzzle in physics about why there's this certain type of symmetry in the universe when, in theory, there shouldn't be. Like, imagine flipping a coin and it always lands on heads. It's possible, but the odds are super slim.
Right.
And the axion swoops in to explain why this coin flip seems to be rigged. The really cool part, this same particle that's supposed to solve this whole other puzzle, it could also be our dark matter. It's like a two-for-one deal.
It's like it was meant to be.
Yeah.
So we've got some researchers setting traps for these axions, these ghost particles. But then there are others looking for something even wilder, primordial black holes.
Now we're talking black holes.
I know, right? But I thought black holes formed from collapsing stars. What makes these primordial ones different?
Okay, so these primordial black holes, they're thought to have formed way, way back, like right after the Big Bang, when the universe was this crazy, hot, dense soup of energy. Imagine tiny black holes, some maybe smaller than an atom, just scattered throughout the universe, like leftover pieces from the Big Bang itself.
So instead of from stars, they were just there from almost the very beginning.
Yeah, but they're so tiny, how could they be dark matter?
That's a good question.
Well, they could actually come in lots of sizes, from those little specks to ones way bigger than our sun. And because they formed so early on, there could be tons of them, maybe even enough to explain all the dark matter we observe.
Okay. But if they're that small and that old, how do we even find them? It's like looking for a needle in a haystack.
Exactly. And the haystack is like the entire universe, right? But scientists are getting creative. One way is to look at how these black holes might bend light from faraway stars. It's a tiny effect, but it's there.
So we've got axions, we've got black holes from the dawn of time. It's all pretty wild.
Yeah.
But then there's a whole other group of researchers asking, what if we need to rethink gravity itself?
Right. Modified gravity. This is where it gets really interesting. What if, instead of looking for a new particle, we're wrong about gravity?
Wow. So not what dark matter is, but how gravity works. That's a huge shift in thinking.
It is, and there's this theory called MOND, modified Newtonian dynamics. It basically says that gravity doesn't work the way we think it does at huge scales, like galaxies. It's like the rules change when you go from playing checkers to playing chess.
So this change to the rules, that helps explain those strange galactic rotations we talked about earlier.
Yeah. MOND actually predicts the rotation of some galaxies really well, which is kind of amazing. But like with any good theory, it needs to explain all the evidence. And that's where MOND and those other gravity theories run into some problems. They might solve one puzzle, but create a new one somewhere else.
So it's like fitting a square peg in a round hole.
Exactly. You might get it to work sometimes, but it's not a perfect fit. And that leads us to this really fascinating point in dark matter research.
It's kind of a stalemate, you know? We've been looking for these particles for decades. Nothing. But then you've got this other idea of changing the laws of physics, which is a big deal.
It's a tough choice, right? But here's the thing. Both paths, they lead to something brand new. Finding a new particle or changing how we think about gravity, that would be huge.
It would totally change how we understand the universe.
Mm.
You know, looking at all this, it really hits you how the hunt for dark matter has just, like, pushed science forward.
Absolutely. It's not just, let's build a bigger detector. This search is impacting other fields too. Astrophysics, quantum stuff, new telescopes, new experiments, all because we're trying to understand this invisible thing.
It's incredible. Human curiosity leading to these unexpected breakthroughs. But even with all that, we still have so many questions. Like you said before, what if dark matter isn't a particle at all?
Yeah, it's a thought,
What if
right?
it's something, I don't know, more fundamental, something that changes everything we thought we knew?
It keeps you up at night. Like, what if all this searching, all these experiments show us that dark matter, it's not just a missing piece of the puzzle? What if we need a whole new puzzle?
Whoa, that's a lot to process.
Yeah.
It's humbling, you know, that we might be completely off.
It's like we're explorers heading out into the unknown. No map, no clue what's out there.
But that's what makes it exciting. Who knows what we'll find?
Yeah.
So to wrap this all up, we may not have the answers about dark matter just yet, but what we do have is a much better understanding of just how much we don't know, and honestly, that's pretty cool.
It is. It's about the journey, the exploration.
Exactly. Keep those questions coming. Keep exploring. And hey, maybe you'll be the one to finally crack the code of dark matter. Until next time, happy deep diving.